Thank you very much. Well, thank you very much. Thank you all for coming, and certainly it's a great pleasure to be here. So what I want, well, if you guys don't mind, I think I'm going to turn off the video just in case the bandwidth is not enough for the whole household. Okay. So what I'll be talking about is some of a sort of an overview of some of our recent progress in the area of tensor completion, basically specifically how to exploit the row rank structure of tensor, a high dimensional tensor, in order that we can complete the whole tensor just from partial observations. And these are based on joint work with my longtime collaborators, Dong Xia from Hong Kong University of Science and Technology, and Chen Hui Zhang from Rutgers University. Now, let me start with a sort of a very quick background, I guess, for this particular audience. I probably don't need to say much about it. We've all seen how tensor methods are becoming so popular nowadays in data science, mostly because we are collecting more and more data with more and more structures. So here just a sort of a selective list of some of the examples. One thing I do want to emphasize is here, actually, I will be a little bit casual when I talk about tensor, because oftentimes really what I meant is just a multilinear arrays. But nonetheless, it's probably bad scholarship on my side, but nonetheless, just being lazy, I'll just probably use this interchangeably. But nonetheless, the issue is with this sort of a multilinear arrays, when tensors, however you want to call it, with this sort of a rich structure in the data, it offers a lot of new opportunities for data analysis, but also at the same time, it creates new challenges. These opportunities and the challenges, they manifested in different ways depending on the context. So what I'm going to do today is actually taking a very specific problem, as many of you are probably know a little bit about. I will explain in further detail. That's the problem of tensor completion. So I'll use this particular problem to illustrate some of the new opportunities when we move from the classical matrix-based approach to tensor-based approach, and some of the new challenges and the new behavior. So this is a quick overview of some of the things I'm going to talk about. So I'll start by first precisely define the problem. What I'm interested in here is a tensor completion. I'll look at sort of one of the simplest form of the problem. And then I'll discuss specifically 3 different methods that can be classified into 2 different categories. One falls into the class of methods, so-called convex methods, and the other is the non-convex methods. So I'll discuss some of the pros and the cons of each of these methods before concluding the talk. So let's start on the problem. The problem actually is fairly simple. As many of you probably have heard of the problem, tensor completion, or probably it's a simpler cousin, the matrix completion problem. And one of the main motivation is in the context recombiner system. So of course, in the case of matrix completion, this is often related to when the Netflix prize. So the idea essentially is we have millions of users watching. Of course, there are millions of movies possibly. And obviously, each user can only watch a selected few movies, and each movie certainly cannot reach all of the users. The idea is if you look at this matrix in a sort of which, well, actually is more precisely, it's a rating, which one likes which movie and so on and so forth. If you have a partial observation of this matrix, is it possible that we can fill in the blanks? That's the main idea here. And certainly we can extend this beyond just the users and items. Oftentimes nowadays we call context-aware recombiner system, kind of like this illustration you have here. You have different items, you have different users, and they may be, say, for example, context, like in this particular case, different features you are looking into. And so you may have a few observations on this particular third order tensor. And the idea here is, well, how many observations do you need to make about the entries of this third order array before you can recover the whole thing? And this is the basic idea. But nonetheless, we are going to take a little bit of abstraction so we can talk to the basic mathematical problems behind it. The basic idea is as follows. Suppose I have a true tensor, let's call it a T. And what I'm going to do is, for simplicity, in this talk, I'm going to focus on cubic tensors, meaning that I'm going to look at a third order tensor when each of the direction of a size D, each mode has size D. So What I had in mind is the situation when D is very, very large. That's typically the case when we have the sort of high dimensional problems. And then what we're going to do is suppose you can randomly sample the entry from this cubic tensor. So these omega i's are the indices. So of course, obviously we have 3 different indices. To put it a little bit more mathematically, basically these omega i's are taken uniformly from these sort of different three different indices from 1 to D. And what I'm going to do is I can observe this particular location. When a given index, I can observe the entry. And suppose I observe n entries. The question is, how big does n need to be before I can recover this original tensor T from these pairwise observations, the indices, and also the particular value at that entry? Of course, there are 2 things that come into play here. Well, 2 essential concepts here. One, this tensor needs to have some structure before we can recover. Well, if we are hoping to recover it when just a partial observation. One of the common assumptions is that this tensor really is of low rank. I'll be a little bit more precise what we mean by low rank in just a couple of slides. But nonetheless, the main idea is the degrees of freedom needs to be a little bit smaller so that we can recover it from partial observations. The other essential concept is the so-called incoherence. The idea basically is because I'm randomly sampling entries, imagine if I have a tensor which just have 1 non-zero entry, then if you do random sampling, if you miss that entry, then you miss it. You cannot recover it. So in order to avoid such situation, what we're going to assume is that each entry of your tensor carries a similar amount of information, and more precisely, this is the concept of incoherence. Essentially, I want to make sure that I should be able to recover the tensor and not even if we miss some of the entries. But nonetheless, it's helpful that we first look at the simplest situation, which is matrix completion, just to gain some ideas on how we would approach this problem. So the basic idea in the case of matrix, just to reiterate a little bit, can be illustrated by this figure here. Suppose I observe a matrix on the left-hand side, and only the colored entries are observed. So the blank spaces are the ones I don't get to observe. The question is, how can I recover the original matrix, which is on the right-hand side, just by looking at these partial observations? Well, one thing to be sure, there are infinitely many matrices that could agree with all these observed entries. But one thing we had in mind is these 2 matrices need to be of low rank. And the lateral idea would be, I want to look over all the matrices that agrees with these observed entries, the ones that has the smallest rank. Well, it turns out computationally that's a difficult problem. So one of the most popular approach is this so-called nuclear law minimization. So instead of minimizing the rank, I will instead minimizing the nuclear norm of this matrix. So again, the nuclear norm of the matrix is just the sum of its singular values. So if you think about it, this essentially can be viewed as a convex relaxation to rank, because rank is a number of non-zero singular values. And so the nuclear norm is a sum of the singular values. So it's kind of like L0, L1 type of relaxation. So what I'm going to do is I look for over all the matrices M, which agrees with whose value on the observed entries agrees with whatever I observed. But over all these matrices, I'm going to look for the one with the smallest nuclear norm. The main benefit of this is, again, because the nuclear norm is a convex function of M. So this becomes a convex optimization problem and can be solved fairly efficiently. Not only that, you can show under some conditions, like I mentioned before, like incoherence, this type of conditions, you can recover the true matrix T when this many observations. Basically, you need to have N is the number of observations, basically how many entries on this side. This needs to be of the order R multiplied by D and up to a logarithm factor of D. Again, let me emphasize, because we're focusing on a situation when the matrix is large. So basically what I had in mind is D is very large, but R is very small. So what is R and R multiplied by D? This basically is degrees of freedom for all the rank R matrix of D by D. So essentially what this says is, well, you give me a matrix which is rank R, its degrees of freedom is R multiplied by D. So I only need to have extra factor of log D before I can use a convex optimization problem to efficiently recover the original matrix from just partial observations. So this is what we know for matrices. And naturally, of course, at least at the first sight, this looks like a very innocent task. How do we extend this from matrices to tensors? Well, to begin with, the very first thing we need to address is how do we formulate the concept of low rank list? And when it comes to higher order tensor, obviously, well, since in this particular program, of course, we probably have heard a lot. There are many different ways you can define ranks for tensors. Turns out one useful notion for us in this particular context is the multilinear ranks. Just to quickly refresh your memory here, the multilinear ranks is basically looking at the linear spaces spanned by the mode, well, by the fibers from different modes. For example, if I have a third order tensor, like what we're doing here, you can look at all these entries looking by fixing two indices and let the third index vary. So I end up with a bunch of vectors of this form. And then what I can do is I can define one rank to be the dimension of the linear space spanned by these fibers. Of course, I can look in three different ways. I end up with three different ranks. And so this is typically referred to as the multilinear ranks. And this is closely related to the Tucker decomposition of a tensor. Basically, suppose you have a third order tensor. Suppose you have the multilinear ranks R1, R2, R3. What this allows you to do is basically you can decompose this tensor as three, basically these are changeable bases, U1, U2, U3. You can think of this as orthonormal matrices. So basically these will be the changeable bases, and then you have a core tensor, which is only of dimension R1 multiplied by R2 by R3. So what we're going to do when we say we want to recover low rank tensor, this is the basic problem we have in mind. Suppose we have a tensor T. Its multilinear ranks, for simplicity, all three of them are upper bounded by a small value R. And what we're asking is the following. Suppose you have a true tensor coming from this site, coming from this particular set. And if we can randomly choose a few entries to observe, how many of them, how many entries do we need to observe before we can recover the true tensor, which the original tensor is of d by d by d? How many entries do we need to observe before we can recover T exactly? And to answer this question, just like in the matrix case, first, we need to understand what's the degrees of freedom of this set. Basically, you can do a simple calculation. The dimension of this set is of the order R to the cube. This represents essentially the degrees of freedom for the core tensor. And RD, this represents the degrees of freedom for the three U1, U2, U3, the three sets for changeable bases. So ideally, if we look at the situation in the case of matrix, ideally what we're hoping for is the sample complexity, meaning the total number of entries we need to observe before we can recover two. Ideally, we are hoping that is going to be essentially of order R cubed plus RD. And just like in the matrix case, we can probably live with a logarithm factor of D. Nonetheless, we hope we can recover when the sample size essentially of this order. And this, again, as I mentioned earlier, this can be achieved for matrices, especially in particular, using Euclidean law minimization. So what happens when tensors? Turns out in the case of tensors, the situation becomes much more involved. First of all, on the positive side, when tensor structure indeed, you can recover it with a much smaller number of entries as opposed to the matrix case. But then on the con side, what we have is we don't have a clean result like in the matrix case, which essentially tie together when degrees of freedom. I'll explain a little bit. And the gap, in some sense, to some degree, actually is more fundamental than a mere technicality. So what I'm going to do is, again, as I mentioned, I'll talk about three different ways trying to tackle this problem, hopefully just to illustrate some of the new challenges here. Let's start with the first approach. The first approach actually is fairly simple and intuitive. Well, one of the main challenges here is when we deal with higher order tensors, it's harder to characterize the low rank list. Well, not hard to characterize, but hard to take advantage of the low rank structure. And computationally, this becomes even harder. So one simple strategy would be, well, if you have a harder problem, you convert this to an easier problem. The easier problem would be the matrix problem. So suppose I have a third order tensor like illustrated here, I can unfold this into a matrix. Well, this is the advantage of the multilinear ranks. If this original tensor has small multilinear ranks, after you unfold it, you would end up in a matrix, which is of low rank. And we know how to take advantage of low rank list for tensors. Basically, we can do nuclear log minimization. So if we call this M1, M2, M3 as 3 different ways to matricize this tensor, I can minimize the matricize, the nuclear norm of the matricize the tensor, just like before, over all these tensors that agrees with my partial observations. Of course, there are 3 different ways you can unfold. So it's a good practice. You sum up all these 3 nuclear norms. And if you think about it, this is essentially taking advantage of what we know for matrices. And computationally, you can use similar algorithm to do so as well. And the main challenge is what? Imagine your original tensor is a cubic tensor is d by d by d. When you unfold it, this becomes a matrix d by d squared. Of course, the tensor has more structure on how these columns, although they are d squared columns, they need to have further structure. But once you unfold it into matrix, you lost that structure. As a result, what's the degrees of freedom in specifying a matrix which is d by d squared when rank R? The degrees of freedom now becomes RD squared, which is exactly this factor here. And this is much bigger than the original degrees of freedom in specifying a tensor when multilinear ranks upper bounded by R. So this approach is very intuitive, very simple, but nonetheless, we see an opportunity here basically is, well, this degrees of freedom, this sample size requirement may be improved. And how? Basically, we ought to let tensors be tensors rather than converting them into matrices. So a second approach, also very intuitive to try, is we want to generalize this idea of nuclear log minimization from matrices to tensors. And in order to do so, the very first thing we need to do is we need to think about how do we define nuclear log for tensors. And of course, while there are many experts in the audience here, when it comes to higher order tensors, defining nuclear norm, there are multiple ways. And one way that is convenient for us is as follows. Basically, we define nuclear norm as the dual norm of a spectral norm. So suppose I have a tensor A, I can define spectral norm as the maximum inner product between A and the elementary tensor, basically rank 1 tensor, when the unit length, when the unit norm. And once we define the spectral norm, we can define the nuclear norm as its dual norm. So what we're going to do is we're going to do exactly like what we did with the matrices. We're going to look over all the tensors that agrees with my partial observations, but nonetheless, I'm going to look over them and trying to find the one with the smallest nuclear norm. And now you can do a little bit of analysis with it. And this is the sample size requirement we end up with. Again, this is a lot quite close to what we have in terms of degrees of freedom I showed you earlier for this set of all third order tensors when rank up to R. But nonetheless, this already is a significant improvement over the matrixization setup. The main improvement happens here. Again, we're thinking about a situation when R is very small, so we care about the exponent for D, where D is very large. So in the matrix in the previous approach, you get a D squared, and here you get a D up to 3 halves. And I'll come back to these 3 halves a little bit later, but nonetheless, here I just want to very briefly, maybe in 5 minutes or so, explain a little bit how we can get this result. The main reason I want to do so is because I want to highlight, although this approach seems very similar, and of course, intuitively, this is motivated by what we know about the matrices, the analysis actually turns out to be quite a bit different, although the overall architecture is similar. It's still like how to analyze convex optimization problem, but the technique is quite different in the following sense. One, in the matrix case, the matrix nuclear law is much better understood than tensor nuclear law. If we want to analyze this convex optimization problem, the strategy is actually very simple. You want to find what we would call dual certificate. Basically, the idea is as follows. I want to show if I want to say this approach works. I want to say, well, the true tensor is the unique solution to this optimization problem. And so what I needed to do is to find a dual certificate to certify that indeed T, the true tensor, is the unique minimizer here. In order to do so, you need to do two things. One is you need to, because I'm minimizing a functional here, you need to be able to characterize the sub-differential of it. Of course, if this is differentiable, basically this is kind of like a first order condition. But since this nuclear norm is not differentiable, we need to be able to characterize this so-called sub-differential. Two, because of these constraints, equality constraints, I need to find a sub-differential that essentially actually is supported only by these sets. Basically, this is sort of a Lagrange type of argument. So this is the overall architect, but this creates two challenges that are quite different from matrix case. The first one is how do we characterize the sub-differential for the nuclear norm? In the matrix case, this relies heavily on singular value decomposition for matrices. For tensors, actually, we are shooting for something a little bit more complicated. The main reason is we don't have a closed form, like in the matrix case for the nuclear norm. But nonetheless, we come up with a sufficient condition for the sub-differential tensor nuclear norm. And secondly, again, as I mentioned, because we want to find a member from the sub-differential that's only supported on those entries we observed. And those entries, as we begin with, they're uniformly sampled. So here, what we need to do is a little bit of probabilistic tool, which is to have concentration inequalities for tensor martingales. And this actually turns out there's a significant difference between the matrix case and the tensor case. Here, for the interest of time, I won't go into the details, but nonetheless, I just want to highlight these two facts. That one, for the sub-differential of tensor nuclear norm, you have very different behavior than the matrix case. Two, we talk about the concentration behavior, and the concentration of a sum of independent tensors turns out to have different behavior in this particular case when compared with the matrix case. So now we have two approaches here. One is the simple matrices. Let me add let me just spend 1 minute add a quick remark here. I just want to emphasize here, I'm focusing primarily on third order tensor, but nonetheless, this idea could be generalized into higher order tensor. And there is actually an interesting twist, so that's why I want to briefly mention this. You can extend our arguments in a sort of a naive fashion to end up in a sample size requirement for kth order tensor to be of the order D up to K over 2. But turns out this can be improved. This can be improved with a more sophisticated argument for the tensor nuclear norm, when the sample size requirement stays at 3/2, regardless of the order of the tensor. So you can have very large K as long as it's finite. And the number of entries you need to observe by using this nuclear norm minimization is always proportional to a factor in terms of D up to 3/2. Nonetheless, here's one issue I want to emphasize here, is this 3/2, this doesn't depend on K. So even for higher order tensor, the sample size requirement essentially, if you view this rank as finite, then basically essentially your sample size requirement for higher order tensors is comparable to third order tensors. So you don't need to suffer even more curse of so-called dimensionality as the dimension of the tensor increases. But nonetheless, let's just take a quick look at the two approaches, the two convex approaches we discussed. Obviously, both of them are still a little bit far away from the gold standard. One is the matricization approach, which end up giving me D² sample size requirement, but the advantage is it's very computable. And then I talked about nuclear norm minimization, where you have sample size essentially depends on D. 3D up to 3/2. This is an improvement, but nonetheless, this comes with a heavy cost. The cost is on the computational side. How to compute the Euclidean norm itself is already very challenging. Not to mention, here we are minimizing the Euclidean norm. So in a way, this approach, although it's convex, is not really feasible in practice. So naturally, this leads to many different ways, many different new areas of research. One area in particular is to think about further relaxing the Euclidean norm minimization by using, for example, the theta norm or the sum of squares relaxation to the Euclidean norm and so on and so forth. There are some recent progresses in these areas. Actually, it's a very exciting research area. But nonetheless, the main challenge with this is either way, even if you do a relaxation, you end up in a polynomial times computable method. They are more polynomial computable in theory than in practice. Because in practice, what at least all boils down to is you need to solve a gigantic semi-definite program. And that's not very practical. Then on the other side, in practice, what people often realize is, well, forget about this sort of a so-called convex approach with a very good theoretical guarantees. Let's just try naive and brute force non-convex optimization. And oftentimes they work really well. So the question naturally becomes, the third approach I'm going to briefly talk about is if we stick with non-convex approach, how well do they do? And why do they do well in some situations? Well, to understand this, let's look at a specific one. This is probably the most straightforward non-convex approach. Again, I have the two tensor T, and I observe them on omega I. These are different entries. So naturally, what I'm going to do is I want to look for all the possible tensors from my set. This set of tensors with ranks upper bounded by R. I want them to match my observations as well as possible. So I end up in this squares problem, basically. Well, for any tensor with multilinear ranks upper bounded by R, it can be characterized by these three sets of changeable bases and a core tensor. Because the core tensor is of the dimension R by R by R, R is small. So once you give me these changeable bases, I can compute the least squares to get the core tensor. Basically reducing this problem as the least squares, just in terms of these three Grassmannian, W1, W2, W3.
I Ming, just wanted to let you know you only have a couple more minutes in your scheduled talk time, but you can use a little bit of your question time if you need.
Sure, thanks. I should be able to finish in a couple of minutes. Thanks.
Okay, perfect, thanks.
So nonetheless, so basically if we come back here, we just need to do a minimization over three arguments here, W1, W2, W3. And this nonetheless looks a little bit intimidating, but nonetheless, this is a very smooth optimization problem. And there are a lot of approaches you could apply to minimize this. But the main challenge here is this is a highly non-convex problem, although it's smooth. So what we can say oftentimes for this sort of highly non-convex problem is, well, if you apply a smooth optimization technique, if you start with a good initial value, you can end up with a good solution. And this is indeed true. So our first result characterizes that. Basically, this says, well, this is, again, this probably looks a little bit familiar now, is D up to 3/2. As long as your sample size is large enough and you start to somewhere close to the truth, then this will converge to the truth. But then the issue is basically the chicken and egg problem. How do I start with somewhere close to the truth? And this turns out has to do to sort of emphasize the issue of initialization. So you can apply all this smooth optimization technique because of the non-convexity. The most challenging issue here is not so much about which optimization algorithm you use, but how you choose your initial value. The main idea here, because I'm running out of time, so I'll be very brief here. The main idea here is you want to do spectral initialization. But the one thing I want to emphasize here is you don't want to do naive spectral initialization. by converting this into matrices and then take a singular value, singular vector. You want to do a little bit more sophisticated one. Basically, to put it in a different way, instead of estimating the singular vector of MT, you want to estimate the singular vector or eigenvector of MT multiplied by its transpose. Obviously, if you load T, the eigenvector of this matrix and the singular vector of this fat matrix, they are the same. But since we only have partial observation, this results in different estimates. And turns out, if you use a more clever way to estimate the product, then you can end up with a better initialization. Putting everything together, this is how you end up with a sample size which is essentially comparable to Euclid law minimization. But nonetheless, this is more computationally feasible. So because I'm running out of time, I'll skip this. Basically, this is, so far I'm talking about the exact recovery, and even with noise, we could do something about it as well. Just to quickly summarize, here actually I talked about 3 different ways of tackling the low-rank tensor completion problem. The first one is just unfolding the tensor into matrices and treating this as a matrix completion problem. It's very easy to compute, but it ends up with a suboptimal sample size requirement. The second one is Euclid law minimization. It's computationally infeasible, but this essentially gives us a benchmark on how well any of the follow-up methods or the relaxation method could achieve. So far, this achieves the best sample size requirement, but then again, this is just a benchmark. Probably the approach to use of most practical value is the last one I talked about, is non-convex approach. It's tractable, and the sample size requirements is close to the Euclid law minimization, at least in terms of the leading term, depending on D. But nonetheless, probably one of the main message I want to emphasize here is because of the non-convexity, we ought to pay more attention to initialization. So with this, I'll stop. Thank you very much for your attention.